Okay, we're recording. Back to share screen to here and there. Alright, so this week's lecture is on intermolecular forces. In fact, this lecture is a little bit odd because it's actually in two parts. And the first part is on how molecules stick to each other. And then the second part is actually on gases, where they don't stick to each other. So this lecture is actually in two separate bits. So this first bit is on how molecules stick together. Now, your notes, and indeed the recorded lecture, didn't have this right at the front. But because I was told I had to put in all this stuff here about tutorial recording, I thought while I was at it, I would go into the lecture and actually cherry pick out the most important points in the lecture in just one or two diagrams. There it is. That's it. Okay, so, well, at least the first half of the lecture. So, what is all this? Well, what it's saying is this. Now, what we're thinking about here is, number one, it's molecules. And the next thing we're thinking is, well, molecules themselves don't have a charge on them, right, by definition. If they do have a charge on them, then the proper term for them would be a polyatomic ion. So we're only talking about things that don't have an overall charge on them here in this particular lecture, okay? So some of this stuff you've encountered before, right? So here's an example here where we've got the molecule HCl here, and you know that chlorine has got, it's quite electronegative in relation to this hydrogen here, and so the electron cloud in the molecule gets pulled over towards the chlorine here, and we could write a delta minus around that chlorine there, saying it's that electron cloud's pulled a little bit more towards it. And of course we could write a delta plus. We could put a delta minus here, and we can put a delta plus here like this. And then of course same argument over here, delta minus, and this one would be delta plus here like this. And what we're saying here is, whilst the molecule overall does not have a charge, within the molecule there's these small regions of negative and positive charge here. And the other thing that's important to understand is that these small regions of negative and positive charge are permanent, right? So I don't think it, and we've done this, we've looked at HCl quite a few times, and I don't think that we have, we need to say much more than that, right? You realise that they're permanently delta minus, delta plus, and then you would realise then that there's a force of attraction here between the negative and the positive here, and that's what's making these types of molecules stick to one another. Now, when I say stick, I don't mean completely contact one another, but really be forced very close together, okay, or pulled together. So what were the take-home messages? You've got to have differences in electronegativity. They're permanent, and that's what makes those molecules stick together. Okay, now the other way in which, now these molecules, as you know, any molecule like this is referred to as being polar, right? But of course you also know there's molecules that are not polar. And in this lecture, we're asking ourselves the question, how do non-polar molecules stick together? Well, they can't do it via this. They've got to do it by some other mechanism. And the way in which they do that is they actually form a dipole, not dissimilar to here. Okay, but the difference is that this dipole here is temporary. Okay, and if you imagine for a moment that can occur, that you get this temporary dipole here, then you're back to a similar situation like this, except the big difference is when this electron cloud is over here and this is temporarily delta minus, it actually pushes this electron cloud and this neighboring molecule away from it. And of course, then this then becomes delta plus here, and that causes that attraction between these molecules here. So we actually have a model for what the two groups of molecules. I mean, molecules are either polar or they're not, right? There's nothing in between there, okay? And that's really the guts of this whole lecture here. So if we move on here, now what I like to do sometimes is actually go back and look at the past a little bit. You saw this diagram here in lecture 1, right? And way back in lecture 1, I said to you, okay, well, you can imagine you've got these particles here. I didn't want to call them anything. I just wanted to call them particles. And now you know, of course, that the two main types of particles that we're considering here are going to either be molecules or they're going to be ions in ionic compounds. That's all there is, right? But for the solid, the liquid, and a gas, obviously they're getting progressively further apart here, and they're doing so as you increase the temperature. Now, of course, when you transition from being a solid to a liquid, that's what we call melting. So that temperature there is the melting point. And when you transition from a liquid to a gas, that's called boiling. And so therefore, that's the boiling point. Now, what I want you to do, and I did say this way back in lecture 1, what I want you to now do is to look at it another way and realize that as you're raising the temperature, you're essentially forcing these things apart. And so therefore, the higher the boiling point and the higher the melting point, the better these guys actually stick together, right? So the boiling points and melting points, if you like, I shouldn't really say this since I'm recording it, so it's there for posterity. The boiling points and melting points are your sticky meters. They're telling you how well those molecules actually stick together. Okay. So last week we looked at one other concept to do with molecules and their polarity, and that is their shape. So early on in the semester we were only interested in bonds and whether or not they had delta minus and delta plus going on. But you now realise from last week's lecture that if you look at a molecule like this, which is carbon dioxide, these are the oxygens here, and of course that's carbon there in the middle there, that these oxygens are much more electronegative than the carbon, and they're pulling the electron cloud over towards them. However, because they're pulling equally and because that molecule is perfectly symmetrical, there's no resultant disturbance to that electron cloud there. And so even though you could say the bonds are polar, the polarity of the molecule is such that it's not polar, it is non-polar. And that's what we did last week, which is something we have to think about as we're doing this stuff. So there's the idea there with those vectors cancelling each other out, those bond dipoles there. Okay, so what does all of that mean? Well, if we tie all this together, carbon dioxide, then you would expect at room temperature, that is at 25 degrees, that temperature would be well above its boiling point, and so therefore you would expect carbon dioxide to actually be a gas at room temperature, and it most certainly is. We're breathing it in and out as we speak, or as I speak, right? Now, if we go to a molecule that's a similar size, like water, it's close enough to this same sort of size-ish, right? It's a bit smaller, but anyway. This is a different situation because although we've still got these polar bonds like this, the difference is because of the shape of the molecule, those vectors don't cancel each other out, and that molecule there is polar. Well, if it's polar, that means it's got permanent dipoles, and so therefore you would expect the molecules to stick to each other, right, to be drawn to one another much more strongly than they would in this case here, where there's no permanent dipole. And as you know, that's indeed the case. In fact, not only is water a liquid at 25 degrees C, it's a liquid below 100 degrees C. So those molecules there are very sticky to each other indeed, right? Okay, but then that begs the question, what's actually holding CO2 together? How do these molecules want to stick if you drop the temperature low enough? Now, by the way, I fully understand that carbon dioxide is a bit of an odd substance in that at 1 atmosphere pressure, it actually goes straight from a solid to a gas, but my arguments are still holding here, okay? And that's got nothing to do with it. That process of what's called sublimation, it's got nothing to do with what I'm talking about here. Okay. So, what are these forces called that hold molecules to each other, right, that draw them together? And the general term for this is van der Waals forces. Okay, so we're not talking about net charges on things. We're just talking about generally these neutral molecules and the way in which they're drawn together. Now, they're either drawn together because of permanent dipoles, which is what I've already been talking about, or they're drawn together by temporary dipoles, which is what I showed you in that first slide there, right? The title slide, if you like. So, of course, if we're thinking permanent dipoles, we're thinking polar molecules. If we're thinking temporary dipoles, we're thinking non-polar molecules. Now, we also need a name for the forces that tend to draw these molecules together. Not the nature of the molecules, but the forces themselves. Now, this, unfortunately, is ridiculous. Okay, now I didn't do this, I didn't invent it, right? I mean, if I'd invented it, well, I pity the world. I would have called them something like non-polar molecular sticky forces, right? But I'm not allowed to do that, right? So thank goodness for I'm sure the whole world's breathed a sigh of relief there. So what they're referred to as is London dispersion forces, but I just want you to be aware they're also known as London forces, which I didn't actually write in there, silly me, or dispersion forces, or temporary dipole-induced dipole forces, which I'm going to talk about a little bit in just a moment as to why they would be called that, because that is actually describing what's going on, what actually gives rise to the force here. Okay. Examples. Pick anything you like as long as it's not polar. Okay, because that's what this is all about on this side, right? So what have we got here? Well, we've got helium. Well, helium gets around as a molecule by itself. It's one atom, it's monatomic. And of course, it's not polar, right? How can it be? Because that whole concept of polarity has to do with at least two atoms somehow engaging in one another and getting more than their fair share of electrons. In this case, there's only one, so there's no way it can be polar. Okay, CO2 we looked at, right? And so your job here is to look at CO2 and go, yeah, I get it. That makes perfect sense that molecule is non-polar, right? So you really need last week's lecture. So has everyone got the idea? Okay. CH4, well, carbon-hydrogen bonds are non-polar anyway, so anything that's a hydrocarbon, that is, contains carbon and hydrogen, is non-polar. We're done. Okay? Now, if you can't remember that, don't worry about it. Grab your periodic table and other information, and if you have a look at the top in the middle there, You know my little graph? In fact, I'll get it for you here on my little table thing, whatever it is. Oh, goodness, I've got to go over here and do this. Where is it? There it is. And then it goes back over here. Zoom's got a mind of its own when you're using dual screens. Okay. So when you have a look, where's that? Silly, oh, there's got to tell you, I don't think Adobe's the easiest thing to use either, by the way. Okay, so here we go. So see over here, I've got bond polarity there for you. You don't even have to remember it. Carbon, hydrogen, non-polar. Ta-da! Okay, so when you go back to here, anything that's a hydrocarbon's non-polar, we're done. What about this one, carbon tetrachloride? So do you remember me last week or Rio saying to you, well, carbon-chlorine bonds are polar, but the molecule is a tetrahedron, right? So if I go, oh goodness me, where is it? No, that's not it. Sorry, gotta go. Where on earth did it go? Go back to here again. There it is. Okay, weird. All right, so remember last week we looked at shapes, and I've actually put the type molecule in there being methane just as an example, but carbon tetrachloride, CCl4, same thing, it's a tetrahedron, the thing's symmetrical, they cancel each other out, carbon tetrachloride's non-polar, okay? So, go back to here, all these guys are non-polar, okay? I just wanted to make sure you hammered last week's lecture. Okay, so let's go over to the other side where we're talking permanent dipoles. So all good, we've already talked about HCl, etc. And there he is there. And I put another one in there, there's oxygen difluoride. So you've got oxygen in the middle with fluorines like this, it's definitely polar. Okay, but there's another class of permanent dipoles in here that are in literally a class of their own, okay? And these are the things that arise because of hydrogen bonding. Now, we're going to have a look at that in a little bit of detail in a minute, but basically the idea is this, okay? We've got hydrogen involved. Gee, that's surprising given the name, right? And then we've got these three guys, NOF. So I want you to remember NOF. So every time, maybe I shouldn't say this, every time you look at me, think NOF. What a NOF, okay? Nitrogen, oxygen, fluorine. So what's so special about them? They're the three most electronegative elements in the periodic table. And if you're not sure about that, go back and where on earth did my Adobe thing go again? Anyway, if you go back into the periodic table and have a look, you'll see I've even written that in for you as well. Nitrogen, oxygen, fluorine, the three most electronegative elements of the periodic table. Okay, why are these so special? Well, there's two reasons, one of which I'll show you a little later, but one of the primary reasons is because these are the most electronegative elements in the periodic table, which means in the universe. And I'd hope you'd also, when you look at your periodic table, notice that the ionization energy electronegativity of hydrogen is actually, what is it? Is it 2.1? Because I can't see I'm cheating, I know it's 2.1, I just thought I'd make you look. Okay, so it's 2.1. Can you see there, like hydrogen's a non-metal, right? Yes. Can you see pretty much that hydrogen is the least electronegative non-metal? More or less. It's only 2.1, the poor little thing. Okay, roughly. So it's weakly electronegative. Okay, so look, This poor little guy here is a weakling, right? And these guys, like this is the you know what a marmoset is, right? You know those really cute little monkeys? Okay, there's these little cute monkeys about yay big called marmosets. Cute as anything, right? Hydrogen's like a marmoset when it comes to trying to gather electrons. These three guys are gorillas. So you know who's going to win out here. So that these bonds are therefore highly polar. And that's one of the reasons why these guys then tend to get put into this separate category over here. Okay. Okay, now let's go over to this graph here. Let's try and get our heads around this stuff. Okay, so look, I know this is a chemistry course, right? But ultimately it's a science course, okay? And I want you to realise that we figured all this stuff out from data. It just didn't come out of nowhere, okay? So a typical thing, like here's the problem in chemistry, okay? Atoms are small, ridiculously. Molecules are ridiculously small. The only way we're going to figure out what's going on is to do experiments on groups of them and then get to see how they operate, okay? So what are we trying to do here? Well, we're really interested in what's happening with non-polar molecules, that is ones that don't have permanent dipoles. I mean, the permanent dipole thing's pretty obvious, okay? And in fact, you can see that things have permanent dipoles. Remember last week, there was that thing in the lecture that had it was pretty much a burette squirting material, like a stream of stuff, and you just got a charged rod and moved it near the stream, and sometimes the stream moved and sometimes it didn't. Hey, if it moved, those molecules are polar. What a cool experiment, right? So we've done that. Don't worry about that stuff for the moment. But what we're really interested in is what's happening with these forces between molecules that aren't polar. How do they do this? Well, you're going to pick the simplest models you can, or the simplest experiments you can, or subjects to start with. So the most obvious one to pick, right, is going to be the noble gases. They're only one atom. The argument is one straight away. Those things are non-polar. The molecules are one atom, they're non-polar, that's it. Okay, so what they're doing here is they're plotting boiling points versus atomic radius. Now, how they work this atomic radius thing out, I'm not quite sure from this experiment. I don't really care. Okay? Bottom line is the boiling points go up as they get bigger. That's the bottom line. So that's the first experiment that's going to start to give you a handle on what's happening with these non-polar molecules. Is everyone with me? So I'm going to encapsulate this in a really stupid way and say the bigger you are, the stickier you are. Okay? So that's the first thing. By the way, you didn't need atomic radius here. You could have simply just plotted this as period number. So you know in your periodic table there you got helium's in period 1, it's 1s2, right? So it's in that first shell, right? And then neon's in the second shell, and then argon's in the third shell. And as they get bigger and bigger, they get further away. We did that a couple of lectures ago as well. So you didn't have to go all nuts and plot the size of these things in picometers. You could just simply plot it as period number, and you get this. You come to the same conclusion: the bigger you are, the stickier you are. Okay. Now, someone at some stage is going to come along and say to you, "Look, you've done the experiment with the noble gases. Really? They're not real molecules. They're only one atom. Come on. Let's go next level. Let's actually try to find a molecule that's got 2 or more atoms in it that we know is definitely not going to be polar." Well, the most obvious one to pick or group would be the halogens, right? Because they all form diatomic molecules, and of course every atom in each one of these diatomic molecules has the same electronegativity, and it's easy to figure out. There's no issues with shape. Hey, you've got 2 points, there's a straight line, these molecules are linear, we're done, right? Let's use them. Okay, and again, in this case, they plotted atomic radius. They could have written molecular radius or whatever, or just even period number. It doesn't matter. This time they've done it as melting point, and it goes up as they get bigger. The conclusion's still the same. The bigger you are, the stickier you are. Okay, now we're getting somewhere. So someone then, after all that all those experimental results, goes, okay, now I've got enough data. Let's see if we can come up with a theory to explain all this stuff. So this was from that, I just showed you that slide right at the beginning here. So what we've got here is we've got these two molecules here, right? So where we're going to start is with this guy, okay? So this guy here is, it's a non-polar molecule. These two dots here are the nuclei. And of course, this thing here is supposed to represent the electron cloud. And what they're arguing here, again, is that it's temporarily distorted out in this direction here. Hence temporary dipole unequal distribution. Okay, now first thing I want to say to you is that electrons move around in atoms and molecules at random. Okay, so some people think that at random means that everything's evenly mixed. Often that's not the case. Okay, often random means things aren't equally mixed. And if you don't believe me, get a coin and start tossing it, right? And you won't necessarily always get head, tail, head, tail, head, tail, right? You might get a run of heads, then a run of tails, then a mix in between, etc. So this is a similar kind of idea. And if you still don't believe me, if it's cloudy outside but not too cloudy, yeah, it's not too bad at the moment. Look at the clouds. They're at random. They're randomized essentially, right? Okay, so what happens then? Well, here, as I said before when we first started this, here's a neighboring molecule here. Because the cloud is more distorted over towards this direction here, it's got a slight negative charge on it, albeit temporary, which then pushes the electron cloud in this neighboring molecule away, which means this is now delta plus, and then of course you've got this mutual attraction between these two molecules here. And that's the theory in a nutshell. Now, where people probably get a little bit confused here is the name dispersion force, right? Because the force is meant to describe things being drawn together, not pushed apart and dispersed, okay? Now, the reason for that is because the word dispersion here is just referring to the electron cloud and its dispersion, and the fact that it's randomly dispersed and you do get these temporary dipoles. So is everyone clear on that? Because that's something that often causes people confusion here. Okay, now the important point next is, okay, there's the theory, we've already talked about that. Now, no theory is any good in science unless you've got some predictions that go with it, right? And of course, then you test it out doing experiments and stuff, right? And if the experiments are consistent with what you predict, keep the theory. If they don't, modify the theory or ditch it, right? We're like that. We tend to cotton on to things as scientists and then fall in love with them, and then later on breakups are never good, okay? So what are we predicting? So what we're predicting is this, right? First of all, attraction depends on size. The bigger the molecule is, the more likely electrons disperse unevenly. Makes sense, yes? So the bigger the species you're looking at, the bigger the molecule is, the greater the attractive force between those molecules. In other words, that theory then gives rise to that observation that the bigger you are, the stickier you are. So we're on pretty good ground here, right? Now, by the way, if you're having trouble visualizing all of this, why don't you think about Velcro? Because the analogy is actually a pretty darn good one. If I've got two objects and they're small and you can only put so much Velcro on them, then they can't stick that well together, right? But if I've got two big objects like this, and there's plenty of opportunity for those bits of Velcro to stick, they can stick pretty darn well, yes? Okay. By the way, the analogy is good too, because you can still peel them apart and then stick them back together, right? Which then gives us the idea. You can imagine super easy peel apart Velcro, right? Then I'm sure you've discovered that before and hated it. But then what you've got is you basically got the idea that these molecules held together by these forces must be quite slippery against one another, right? So anything that's non-polar, that's held together by these dispersion forces, tends to be quite slippery, right? And if they're big enough, they'll stick well enough that they're kind of goopy and gummy, right? But still they can slip past one another like this, which is what an oil and a grease is, for example. Okay. So, okay, now that contact area concept in this theory, again, is a good one because, and again, you can think of the Velcro analogy here. Let's say I've got two molecules like this that are this shape, right? Actually, if you're watching this recorded, you can't see what I'm doing with my hands here, but I'm holding them up like this, sort of flat, right? They can contact quite easily and stick reasonably well. Now, if I take my hands and roll them up into a ball like this, you can see there's less contact there, right? So they're not going to stick so well. So we would have to predict then that shape matters. Okay, so there's two things that theory is going to necessarily predict. Okay, back to some data because we're doing science. Okay, so what we're looking at here is the carbon family. We've got carbon, silicon, germanium and tin here. They've all got a common valence of 4. You can see that in the periodic table. And we're most interested in the hydrides of these 4 elements here. So when I say hydrides, I mean that they're covalently bound to hydrogen. Because hydrogen has a valence of 1 and these guys have a valence of 4, what I'm interested in is CH4, SiH4, etc. Okay, that's the first thing. Now what? Okay, well, let's just think about these molecules a little bit more. By the way, these are what are called space-filling models or van der Waals models or something like that. We're more interested in the surface area of these molecules than anything else. Anyway, CH4, methane, what's the shape?
It's a tetrahedron shape.
Fantastic. It is indeed, and if you're having trouble remembering that, go back to your periodic table and other information and look down and you'll see that it's indeed that shape. Well, work the groups. Once we've done methane, we've done silicon tetrahydride as well, correct? And germanium tetrahydride and tin tetrahydride. So they've all got the same shape. Now, if you think back to that theory, that dispersion force theory, what it's really saying in a nutshell is size and shape matter. That's what actually influences how well these molecules are drawn to one another. So my point to all of this is all of these molecules actually have the same shape, right? So we've actually, by doing this experiment, we've taken shape out of the experiment. We're not interested in that because they're all the same. Okay. What else? Well, I guess we could be worried that we're dealing with molecules that might be polar. That's going to mess our results up because we're interested in molecules that are non-polar. However, remember carbon tetrachloride? Those carbon chlorine bonds are polar, but the molecule is non-polar because for that tetrahedral shape, all those arrows cancel each other out and the molecule's non-polar. Aha! It doesn't even matter what the difference in electronegativities are between these elements and hydrogen. Because of the shape of these molecules, I know that they are all non-polar. So that's taken out of the equation. We're not worried about that. Okay? So the only thing left is size. Well, it's not size due to the hydrogens because the number of hydrogens is exactly the same. So the only difference is the size of these atoms here. And as you know, there's the electron configuration, for example, for carbon there. So we're talking about the second shell. For silicon, we're in the third shell. Germanium, really we're in the fourth shell. This guy's in the fifth shell here. And as those electron shells build up, they're getting further and further away from the nucleus. In other words, they're getting bigger and bigger. In other words, as you go down a group in the periodic table, they get bigger. The atoms get bigger. Okay, so now I look over here and I go, well, okay, I'm just going to plot boiling point versus period number, because that's actually a de facto measure of how big these guys are. And look what I find. Yeah. The bigger you are, the stickier you are. Nice. Okay. I love science. Okay, so can't help it, got to do another experiment. Let's try and push this to its limit. So what we're going to do this time is we're going to be not interested in size, we're going to be interested in shape. So size for us means the number of carbon, in this case, the number of carbon and hydrogen atoms we've got. We could have picked any combo here, but we've decided on this one. So this one, all of these molecules have got 5 carbons, 12 hydrogens, so they're all the same size. But they're arranged differently. Now, these are the space-filling models here. It might not be too obvious, but this guy here, neopentane, there's a carbon in the middle like this, and then there's a carbon there, and a carbon there, and a carbon there, and a carbon there. And of course, these then have hydrogens attached to them. I'm not going to draw all them and bore you to tears, but that's basically neopentane, this guy here. And you can see it obviously looks a bit different when you do the space-filling models. Okay, we go to isopentane. It's a bit flatter. I'm not going to draw the next one. It's a bit flatter. And this one here, neopentane, it's just a straight line like that. Now, this squiggly line here is supposed to represent the amount of contact between neighbouring molecules here, and it obviously gets bigger as you go from the analogous equivalent of your hand getting more and more clenched up into a fist, or in this case it's a fist if you're going from neopentane and opening up to form a flat hand like this where you get N-pentane, so it's flatter. So what do we find? The data is clear. The boiling point goes up as the molecules flatten out. The flatter you are, the stickier you are. Shape matters, okay? So all of the data point to this theory being a very, very good one indeed, okay? Okay, now we've done this one to death. Are there any questions? So now we've gone away from the non-polar London dispersion force thing, and we're back to polar molecules. And we've done HCl to death, yes? So are we all good to move on with our lives? Okay, because what you haven't done yet, except in this lecture, of course, that's a bit different, are these hydrogen bonds, which I've already briefly talked about, and it's restricted to hydrogen and NOF, nitrogen, oxygen, fluorine. But first, look, can't help myself, got to look at some of the data. So here's an example here where we've got the nitrogen, oxygen and fluorine families here, and what we've done is we've then plotted the boiling points of their hydrides versus their period number. So remember, as you go down like this, they get bigger and bigger. And if we just did it for H2S, H2SE, so we're over here, H2S, H2SE, H2TE, it goes up. Yeah, well, okay, there might be a little bit of polarity there, but these things aren't actually that much different in terms of electronegativity. It's going up because the bigger you are, the stickier you are, for goodness sakes, right? And you can use the same argument for the other guys. Now, if I'd just shown you this data here, and I said to you, well, what do you reckon the boiling point for H2O would be? H2O you would be tempted to extrapolate down to say here and say, well, I guess that the boiling point's somewhere between minus 50 and minus 100 degrees C. And you couldn't be more wrong, because you know what the boiling point of H2O is. Everyone does. It's 100 degrees C. Now, you get a similar effect with the others, but not as dramatic. So none of them go down, they all go up here. There they are, HF and NH3 there. But H2O goes through the roof. I mean, there's 50 degrees C there. 100's like up here somewhere, right? That's ridiculous. So what is going on here? Well, it's actually not. Oxygen's only the second most electronegative element in the periodic table. You'd expect this guy to have the highest boiling point just in terms of electronegativity. So there's something else going on here as well. So the other thing that's going on are these lone pairs. Now, do you guys remember from last week? Okay, now look, this is HF. This green guy is actually fluorine in this instance, right? Now, if you look at fluorine there, you can see it's got 7 valence electrons, right? Everyone got that? It's got 7 valence electrons. So you got 1 here, you got 6 left, 2, 4, 6 like that. This, in other words, it's got 3 lone pairs. Remember doing that? Okay, go to oxygen here, 6 valence electrons, 1, 2, 4, 6. Nitrogen here, 5 valence electrons, 1, 2, 3, and 1 lone pair there. And so there's definitely the electronegativity thing going on, but the other thing that's a big deal has to do with these lone pairs because this is the sort of thing that goes on, and we use water molecules as the example. It's the best one, right? What's happening here is here's a water molecule. There's a big delta plus there. There's a big delta minus there because it's so darned electronegative, right? But look at this hydrogen here. It's big plus. This oxygen's big minus. Nice, but you've got this lone pair here. A lone pair of electronegative, not nice. Almost, how many electrons do you need for a covalent bond? 2. Oh, almost a covalent bond. Almost. Look at that. And then there's another one there. Okay. Can you see that for every 2 lone pairs in any oxygen atom, there's going to be corresponding 2 hydrogens in a neighbouring water molecule? Okay. So bottom line is, and you can use this analogy again, I shouldn't do this. I will, I can't help myself. Let's stick to Velcro as the analogy. Did you like that? No, that's terrible. Anyway, so imagine, you know how Velcro's got like those hooks and loops in Velcro, right? So imagine, it doesn't matter which way around you do this, but imagine the hydrogens are the hooks and these lone pairs are the loops. Is everyone with me? So for every hook, you've got a corresponding loop. That's going to work nicely, right? Now the other molecules don't have that luxury. For this one, you got 1 hook and 3 loops. So only one of these loops can do the hydrogen bond thing I showed you before. So it's almost like you've got 1 hook and then 3 loops, but you can only use 1 loop. That's not all that effective, right? And over here you've got 1 loop and 3 hooks, which isn't very effective. Water's the only one that's got 2 and 2, and that makes it much stickier, and that's why that boiling point goes through the roof there. Okay, now, what do we know about hydrogen bonds? Well, do the experiment and have a bath. So when you hop in the bath, you know those water molecules move apart, and they move apart relatively easily, right? But you also know they come back together again, okay? So hydrogen bonds break reasonably easily, not that easily, it's still liquid at room temperature, but they also form reasonably easily as well. So everyone with me? You've done the experiment a gazillion times, okay? You know what's going on there. Okay, so what's this thing here? Well, this is DNA molecule, at least a part of it. In fact, a very small part, because it's actually got the 5' and phosphate 3' hydroxy group on it. But anyway, so this bit here is one strand, okay? Now, I want you to just follow this quickly. Can you see that that strand is connected completely? All atoms are connected by covalent bonds. Yes. So that's really strong, right? So you can get these big long strands of DNA, right? But this is the other strand here. It's the same thing. But two DNA strands are obviously connected by hydrogen bonds. By the way, these are drawn terribly here, but don't worry about it. Okay, so the two strands themselves are joined by hydrogen bonds. Now, in a sense, hydrogen bonds are like the equivalent of molecular Velcro, right? You can stick things together, and the bigger the molecules are, the better they're going to stick with hydrogen bonds as well, right? But you can peel them apart, right? You know that, okay? Like if you're using Velcro, it's the same thing, okay? So why do we need this for DNA molecules? Because when DNA replicates, because it's a genetic material, when cells divide, they have to get DNA molecules to replicate. What's happening here is, here's my two strands here like this, and they actually have to peel apart. So imagine they're joined there in the middle by these hydrogen bonds, which are here, right? They have to peel apart like this, and then this strand here becomes the template to make another strand there, and this strand here becomes the template to make another strand there, and that's how they actually replicate. So when you think about it, you don't want to be sticking those two strands together with covalent bonds, right? It'd be like sewing them together as opposed to sticking them together with Velcro, where you can pull them apart when you need to. Now, the last little thing I want to say about this, particularly in this environment with COVID-19, everyone's seen, maybe even had, a swab taken, right? Or you've at least seen swab, you'd like take a nasal swab and stuff to detect COVID-19. What you're doing is trying to get just enough material that you're going to have some COVID DNA on it. Now, the amount of COVID DNA that's on that material is actually very, very small, and you can't analyze it, okay? So if this, for example, was COVID DNA here, there's not enough to do an analysis on it. So what you do first, before you analyze it, is you've got to make more of it. So you make it by doing what I've shown you up here, where you pull the strands apart, and then you get new strands to be made, and then you pull them apart again, etc. Right? Now, you can do that. You can do that in a test tube. So here's my test tube here, right? I've got my COVID DNA in here, like this, and somehow I'm going to have to pull now this is in a test tube. Like in a biological system, obviously you use enzymes, but somehow you've got to pull these DNA strands apart, and then you have some enzymes in there that actually make the new strands, and you've got some raw materials there to make the new strands in that tube as well. Question, how do you pull the strands apart? I remember saying, talking to one of my, when I just finished, I started doing my PhD, and I ran into one of my former high school students, and they said, oh, what are you doing? And I told them I was doing molecular biology and stuff. And they said, oh, and I said I was, cutting up bits of DNA and stuff, and they said, oh, you must have very small scissors. And I said, yep, sure do. They're called enzymes. Anyway, that's all in this tube here. How do you pull the DNA molecules apart? You heat the tube up. What do you do when you boil water? You heat it up, and some of that water turns into steam. Aren't you pulling the molecules apart? And can't you put a lid on top, and don't the molecules re-stick again, forming a liquid? So you can actually pull hydrogen bonds apart and put them back together just by heating and cooling, right? That's what you do. You actually have a machine, the technique's called PCR, polymerase chain reaction. You actually heat, the strands come apart. You drop the temperature just enough that the enzymes work to make new strands, and then you heat again to pull the strands apart. And these machines, these PCR machines, simply heat and cool, heat and cool. That's what they do, right? Pretty amazing, huh? Isn't chemistry amazing? Okay, I'm excited. All right, what else? Well, if you're not looking at the news, watching people having nasal swabs because of COVID-19, what about you put some honey on your bread or on your toast in the morning? Have you thought about it, right? What is honey? Well, honey, it basically consists of molecules like, where is that thing gone? There it is. Honey consists of molecules like this guy here. And by now, at this stage in the course, you can look at this and go, oh, OH groups here. OH, hydrogen bonds, yeah, right? They're pretty strong bonds. You can still break them and stuff, but they're pretty strong. And not surprisingly, you get a substance like this. And this stuff, of course, you can make a honey and lemon drink out of it, because this stuff is also soluble in water because it forms hydrogen bonds with water. And if you go over to this stuff here, which is an oil, which is all hydrocarbon, as I said to you before, all hydrocarbons are non-polar, you would expect that, well, okay, oil's fairly sticky and gluggy, right? It's quite viscous, right? So you would therefore be able to work out that oil molecules are actually reasonably large. Why? Because they're non-polar, they're stuck together with relatively weak dispersion forces. To get them big enough, to get them sticky enough and viscous enough, you're going to have to have relatively large molecules. By the way, if you go and look at something like a wax, which is really a solid at room temperature, waxes are hydrocarbons where the molecules are about 50 carbons in size. They're big enough and sticky enough, they're actually a solid at room temperature. Robert, there are enzymes that do, yeah, the main enzyme, well, in fact, I'll just talk PCR, not RT-PCR. The main one is called TAC polymerase, TAQ polymerase. It's actually a thermostable DNA polymerase, right? It's called TAC because it's actually isolated, or was the genes encoding it came from a bug called Thermus aquaticus. Sounds very Roman. Imagine I was an ancient Roman. I could call myself Thermus aquaticus. That would be bizarre. Okay, enough of sticking. Let's go to not sticking. So let's have a little bit to do with gases, and then this won't take long, and then we can have a break. Okay, so I'm not going to worry about that. Now, a couple of points I want to make to you with gases. Point number one is when you're thinking about things with gases in chemistry, it's really important that you think about the system that you're dealing with. Right now, it's not hard, okay? There's only two systems that are going to operate, right? One is where the container is completely closed like this and can't expand, and it's called fixed volume, and that's what it's normally referred to as in chemistry, a fixed volume container. And look at this here. Can you see these? All of these guys are fixed volume containers. Yes. Okay, so what about the other sort? Well, the other sort is like this. You imagine you've got your container here like this, and this one it's got a piston attached to it, right? So that this piston can move up and the volume can change. And that's the easiest way to think about it, okay? Now, this one is not called variable volume, right? This type is often referred to as constant pressure. Now, the reason for this is, imagine you're heating this up here. As you heat it up, if this piston can move, which way is the piston going to move, up or down? up. In other words, the volume's going to get bigger. So let's say it goes to here, and then you stop. Then you've got it at a particular temperature, and eventually it's going to stop when you stop pumping heat into it, and it's at a particular temperature. But there's molecules in here bashing around inside, right? They're bashing around in here. Why doesn't this keep moving up? Answer, of course, there's air pressure pushing down, right? So for any system with a piston in it, right, what's going to happen is that the pressure will remain constant. It will end up being the same as whatever the outside pressure is, and that's why it's called constant pressure. Okay, so that's the first thing when you're doing anything to do with this stuff. So it's either fixed volume or it's constant pressure. Okay, now a few other things. Next point I want to make is this. You already know all of this. The only thing that's going to bamboozle you, seriously, is going to be the words and the terminology here. I mean, let me ask you, right, if I've got this is a fixed volume container here, and I heat it up, so I'm going hotter and hotter here, what's going to happen to the pressure? It goes up, which is what that thing shows. Everyone knows this, right? You know this. Okay. Notice what could potentially confuse you. I said fixed volume, which is not what you use in everyday language, but now you know what it means. You should be okay. Okay, so now just another point. We're almost done with these. So next point is this. When you're dealing with gases, do not use the Celsius centigrade scale. Okay, do not do it. And this graph here shows you exactly why that's the case. Now, this is plotting the volume of a gas versus, so there's the volume versus the temperature there, and it's in Kelvin. Okay. Now, what was the first thing you have to ask yourself when you're looking at the behavior of gases? What was that? Do I remember what did I say? I said, ask yourself whether you're dealing with fixed volume or constant pressure. Yeah? Okay, so I want you to look at this graph now and ask yourself, what am I dealing with here? Well, obviously the volume's varying, and so it must be constant pressure, right? But really you don't care. All you want to be interested in now is the fact that you've got a piston moving up or down, depending on which way you're going in the graph there. Is everyone with me? Okay, so now if you're over here and you start increasing the temperature up this way, well, that's pretty obvious that the volume is going to go up. Yeah? Now, here's the nice thing with Kelvin. The volume, and indeed the pressure if it's fixed volume, is all proportional to the temperature change as long as the temperature change is in Kelvin. Okay, so from here on in, when I'm talking about gases and I use the word temperature, I'm thinking, and you should be thinking, Kelvin. Is everyone with me? Okay, if I double the temperature, what happens to the volume? Variable volume, fixed pressure in this case. If I double the temperature, what happens to the volume? It doubles. If I keep the volume constant, it's fixed volume, and I double the pressure, double the temperature, what happens to the pressure? It doubles, okay? That's it. Now, if you're wondering what's happened down here, that's because when you've done this experiment, you're dealing with a gas, and at this point you drop the temperature low enough here that the gas is actually condensed into a liquid, and your data's rubbish from here on in because you're not looking at a gas anymore. So the only way you can get a handle past this point here going down in that direction is you have to extrapolate. So that's why it's a dotted line there, okay? Now, you can do this for any gas you like, and it will always intercept there at 0 Kelvin. Okay? Nice. And it's all beautifully proportional. Okay? That's it. They're the basic rules. Okay, so This is just making sure you understand the common sense of this. Okay, so this one here, now in this diagram here, we've got a kind of odd piston arrangement because in some cases the piston doesn't actually move, you've actually locked it in place. So that's what's happened in this instance here. Okay, so it's fixed volume, in other words. Well, if you heat this up, what happens to the pressure? It goes up. And you know in Kelvin it goes up proportionally to the increase in temperature measured in Kelvin. Now you can call it Ammonnen's law if you like. Do you have to remember any of this? No. You know it already, and I don't want you to memorize any of these laws. Okay, so don't worry about it. Okay, go over here to this one. What's happened? Well, this one, obviously the piston's moving. Okay, I push the piston down here. I've decreased the volume. Well, now you've got the same number of molecules bashing in a smaller volume. It's not surprising the pressure goes up, and it's proportional, right? So if you halve the volume, you'll double the pressure. Okay, you know that. Go on, blow up a balloon and then squash it. See what happens. The pressure goes up to the point where you end up... Indeed, Brent, indeed. So you know this stuff. Okay, and this last one, you know this one as well. This one here, obviously, we've decided to use variable volume here. You've pumped more molecules into the system, and again, it's beautifully proportional. The more molecules you have, doesn't matter what they are, and that's a cool thing as well. It doesn't matter what they are, the volume will go up, and of course it's proportional. If you've got double the number of molecules, you've got double the volume. Okay, that's Avogadro's law, but nevertheless you can see the sense in this. And you know this as well, okay? What are you doing when you're putting air in your tyres? Exactly that, okay? To some point, of course, where the tyre then kind of, you can't push it any further in terms of volume, and then it's the pressure that's going up, obviously. Okay. Now, I know some people get a bit psyched out with equations and things. Don't worry about it. Okay, I'm actually, for this one here, I'm going to show you, after we've had a break, how you can actually do questions involving these equations where you don't use these equations. Trust me. Okay, anyway, if you've done chem before, I know you've done a whole stack of the different variations on these, and I thought, let's not worry about doing that. This is the one equation that you can use here. When do you use it? You use it when the number of molecules stays the same. Okay. Now, if you happen to do a question where the temperature's the same, then this and this are the same. They just cancel each other out. And you're left with P1V1 equals P2V2, and then you can rearrange and do that if you're a formula person. Okay? More on that when we do the examples. The only other thing I'd say to you is just be aware, like always, it's so important to make sure if you're doing any calculations to put your units in and make sure they cancel out and you get a sensible unit that's obviously you'd expect, given in this case we're looking at volume, that makes sense, that's in litres. Okay, so I actually want to do more on this when we do the questions. Okay, now there's one we can't really get around too much, and that's this one here. We're going to have to use this one. Now this is telling you what's happening when you can fiddle around with the number of moles of gas. So that the really important thing here to realise is that N is the number of moles. Okay, R is the ideal gas constant. That's it there, and it can vary depending on what the units are here. Now, in your periodic table and other information, you actually have both equations, and you have two versions of R. And if you're wondering which version of R to use, well, obviously it depends on the question. You simply select the value of R that has similar units to up here, and you can't go wrong. Okay. Anyway, again, a little bit more on that one later as well. Okay, time for a break. So, any questions before we have a break for, say, 5 or so minutes? All good? Okay, I'll see you in 5 minutes.
Just me.
Oh, it's you.
Just stopping in my way to my next appointment to have a pee.
Oh, good job I just turned the microphone off.
I've only got 5 minutes.
You're a cat. Look at you and your gorgeousness. Yeah, baby. God, Bailey. I'm just about to start. You know the camera's on. I haven't got the Jules. I haven't got the mic on, so. What? let's... All right, how you going, guys? We're back, ready to go? So, all good? Oh yeah, I think so. Anyone else going to put their camera on? Have they had enough? Oh, terrific. Thanks, guys. Okay, so let's share that screen. And we're talking intermolecular forces. And the online quiz. Okay, let's tidy this up a bit, eh? So it's a bit easier for you to see. Alright, that's better. Alrighty, so anyone got any questions about number 1? Alright, I want to actually walk you through this one. So just a couple of things. So I mentioned before that you can actually solve these questions pretty much without the formula. Now, there's two types of people in this world, those who like using formulae and those that don't. I tend to be in the don't camp. I'm actually going to show you another way of doing it. Sometimes you've got no choice, but let's have a look at what's going on here. So if I get myself, I might get this one, I think. Okay, so what do we got going on? So the first thing you got to do is try and figure out whether we're talking fixed volume or fixed pressure. Okay, so that's the first thing. So we've got 2.5 litres here. Okay, and you warm it up and you're asking for the volume. So if you've warmed it up and you've gone from this to some other volume here, it's obviously fixed pressure. That is variable volume. Yeah. So I always like to think of it, again, as a piston like this, right? So what we're really asking is, okay, I've got 2.5 litres there, right? And then what we're doing is we're going from 196 C. Oh, there's a problem. Celsius. Don't do it. So first thing you're going to have to do is convert this obviously to Kelvin. To do that you had 273. That was in lecture 1, I think I did that. So it's probably a bit rusty for you, but if you look at your periodic table and other information, the formula is actually there for you anyway. Okay, so I'm going to cheat just a smidgen here, and I can look down here and see what it is in Kelvin. So it's 77.2 Kelvin. So what I'm going to do here is go, okay, we're going from 77.2 Kelvin, and we're going to, what are we going to? 100, what have I called that? 373.2, okay, whatever. 373.2, oops, point 2 Kelvin. Okay, now the way I do it is I just go, well, I've increased the temperature by this much, the volume has to go up proportionately. Well, how much did I increase this by? I increased this by 373.2 Kelvin over 77.2. Kelvin equals 4.8. Okay, so the temperature's gone up by 4.8 times. So what happens to the volume? Well, the volume must have gone up. The volume must have gone up by, the volume must be equal to, it's gone from 2.5 litres, it's gone up by 4.8 times, equals 12.1 litres. Okay. I didn't use a formula. Okay. I don't care which way you do it. I guess the reason I kind of I prefer doing it the way I just showed you is because you really understand what's happened. You've heated a gas up and the volume's gone up and you're just trying to figure out how much proportionally. So, but I get it. Some people don't like doing it that way. So for all of these questions, I've actually written out how to do it with the formula. And there it is there. And I don't see any point in spending the tute walking you through this unless, through the formula way of doing this, unless... All right. So, Samantha... So, okay, you said that. So, are you good with what I've written down here then?
I may not have been keeping track. I was trying to do the formula while you're doing that.
Oh, that's terrible. That's all right. So, look, it's there. I mean, what's happening here, of course, is that the pressure doesn't change, right?
Yeah.
Samantha? So that P1 V1 on T1 equals P2 V2 on T2. You don't need the P, right? Okay, so then it's just V1 on T1 equals V2 on T2, and you're after V2. All right, cool. And you got it? Okay, cool. That's all. I just want to double check, all right, because I probably won't do too many more of those with these formula because I've got them there for you to go back, and you can do them at your leisure, check to see that you've done them correctly, and of course you can turn up to the next tute and ask if there's a problem. Okay. Alrighty. Right, let's move on. So that question's similar to the previous one, so no worries. All right, what's going on here? Now, by the way, see this question here? You could also do this without the formula as well. Now, this one here, you're changing, what are we after here? You want the volume and you're fiddling around this time with the pressure and the temperature. Okay, so first thing though to do, regardless of whether you're using the formula, is to ask yourself whether we're talking fixed. What are we doing here? Well, we're varying the pressure and we're varying the volume. Okay, so we're fiddling around with everything here. Okay, but can we kind of figure out what's going on here? I reckon we can. So just watch for a sec. Okay, so let's say we've got our container here and it's got 35.4 litres, and oh geez, I should have written that in as well. And this is 151 atmospheres pressure. That's pretty serious pressure, right? Yep. And then you actually change the temperature from 25 to 37. So let's just write that down here so we can get our heads around this. So you're going from 25, while we're at it, let's change this to Kelvin. 25, that's 298 Kelvin. and that's going to, what's it going to? It's going to 310 Kelvin. So actually, when you convert to Kelvin, can you guys see here that that temperature change isn't that much proportionately? It's only 310. It's 310 K divided by 298 K, okay, which equals, I think that's 1.04. Someone could check for me. I think that's right. So it's not much. The temperature only goes up a tiny wee bit, in other words, right? But the pressure is insane, right? It goes from 151 atmospheres to 1 atmosphere. Okay. Well, if it's going to 1 atmosphere, what must happen to the volume? How am I going to decrease the pressure here? What must happen to the volume? It must be, isn't it going to get less if I increase the volume? Yeah. And isn't it proportional? Yes. It is proportional. So all you've got to do then is go, well, okay, what's happening to my volume then is I'm going from 35.4 litres, whoops, that was very German of me, 35.4 litres, and it's going up 151 times. True? Because everything's proportional. Nice. In fact, there's also a temperature change, and that only makes it go up by a factor of 1.04 equals, and there's your answer. No formula. Isn't that nice? Okay, so, except for Samantha. But Samantha, you've got this one here, right? And so you'll be able to follow that through, and you should be all good, or anyone else. Yeah, Lisa, I tend to see students in the 2 camps. Yeah, that's right, Robert, because that temperature factor is so tiny, it doesn't really matter. But yeah, you're on the right track. Well done. Okay. Now, what about this one? So, what do we got here? We've got a spray can. The can's thrown into a fire. Why would you do this?
Oh, no, this is
Samantha,
brilliant, yeah.
Yeah. Beg pardon?
Sorry.
Oh, Lillian, there you are up there. I'm looking... Sorry.
Calculated the last question. Yeah. I don't know if it's because my calculator's off or if I'm silly, but I didn't get any of the answers they had in the multiple choice there. Yeah,
you didn't get something
it is close. It's about
this one, you mean?
2 numbers off, like 2 ones off, like
So tell me what you got.
Rounded, it's 5,559, which is very close to the third one, but like
that's close enough. Yeah, that's because it's going to depend a little bit on the conversion factor, by the way, that you used for the Kelvin.
Because like the decimal places and stuff.
And ballpark, by the way, I play very fair. So you'll never get a multiple choice where one of them's this and then one of them's 5559. So don't worry about it, okay? Yeah. Okay. So, good point. Okay, so going back to this one here, why you would throw a spray can in the fire is beyond me, but nevertheless. Okay, and it says what will be the pressure in the can. So they're saying here it's fixed volume. And of course, as you heat it up, the pressure goes up, and it goes up proportionally. By the way, don't ask me what torr is. I have no idea. I just found this weird question and thought that's an amusing way of writing pressure, so I put it in. Who cares? Anyway, so what's it going to be here then? Well, it'll be 748. So you can do it like down there with the formula, or just go, okay, what's happening is it's ends up at 748k divided by 296. Actually, if I'm looking at that equals, so the pressure's going to go up by that amount, which is about double. Right, it's actually 2.5. I think this one ends up being 2.5 times. So you multiply 2.5 by 1344 and you'll get that answer there. Okay. Right. Nice. Okay, now this guy here, you are going to have to use the formula. There is actually another way to do it. If you guys have done chemistry before, if any of you have done chem, you might have learned that the volume of 1 mole of any gas at standard temperature and pressure is 22.4 litres, and you could use that to actually figure this out as well, but we're not going to do it that way. So whatever, if you don't understand what I just said, just ignore me anyway. Okay, so we're going to use the formula. We've got to use PV equals nRT. A dead giveaway for questions like this is I normally drop this in here, the ideal gas constant, which you're going to need, right? But the other dead giveaway is it says moles. Okay, so almost certainly we're going to be talking that. So for this one there, we are going to use that formula. And there's the formula there. It's actually asking you for the volume. So you rearrange the equation for volume, plug your numbers in, and you get 217 litres. Okay, any questions? By the way, if you do it the other way, 21 mole is about 20. See, can you see this is standard temperature and this is close to standard pressure, right? So 1 mole of any gas in those conditions occupies about 20 litres. So that's about 10 times 20. Bingo, there it is there, right? Oh, cheers, Merkel, no worries. Okay, binary compounds. All right, so we're now moving away from gases. So group 13, what's the first thing you're going to look at? Periodic table. Group 13. Which one's the top of the... Yep, so what I do, because I like to think in things in concrete terms with examples, is I just go, oh, okay, we're talking something like boron trihydride there. Yep. And if you're having a little bit of trouble with that, if you go over here, that's actually the example molecule I gave you anyway. There it is, just there, okay? So then you've got to go actually think back to last week's lecture and go, oh, this thing's symmetrical. It doesn't matter how polar those bonds are. Holy mackerel. It doesn't matter how polar those bonds are because it's symmetrical. They cancel each other out. They cancel each other out. That means that any molecule that's like that, regardless of what the central atom is, and regardless of what these X's are here, the molecule is non-polar. So when we go back to here, there's your non-polar answer, and then you're back into this week's lecture and you're going, okay, it's non-polar, we're talking non-polar, we're talking dispersion forces, we're talking the bigger you are, the stickier you are. Actually, that's not a very big molecule. It's only got 4 atoms in it. It's not going to be all that sticky, so therefore you would expect it to have a low melting point. All good? Cool. I'm getting sick of doing hydrogen chloride. Familiarity breeds contempt. Have you got any questions, or shall we move on? I feel like breaking up with hydrogen chloride. Okay. All right, that one was from when I ran through that stuff in the lecture. Yep. Okay, group 14, the carbon family. Obviously, you go to your periodic table and you would, well, we did this. I just did that before. Okay, so that's your CH4, SiH4, etc. Makes sense now, right? Okay, this one here, HCl molecules, the intermolecular force is due to, well, it's due to a permanent dipole interaction, which is weak compared to the what's the intramolecular force in HCl? In other words, I'm asking what's the nature of sticking exactly, Robert, spot on. The covalent bond. You got it. So I've done this because every now and then I've got to be a bit hard on you and throw in some of this terminology because you'll see it somewhere else, right? And I don't want, at the end of the day, I don't want you to be intimidated by the words and the terminology, right? In fact, I don't want you to be intimidated by any of this stuff. I want you to get HDs. Okay. I told you it makes me look good, right? Okay. Gas. Okay, so these set of questions here, I'm trying to get you guys to just think through it again. Yeah. Okay. Fixed pressure. Oh, okay. Variable volume. Yeah. Yeah. Okay, that one there, that's just a fancy way of saying, well, okay, I've got these size molecules. You should recognize that all three of those are non-polar. We're thinking dispersion forces. We're thinking the bigger you are, the stickier you are. We're thinking, well, the smallest one is going to have the lowest, what did I want? Boiling point. The lowest boiling point, the biggest one is going to have the highest boiling point. By the way, remember we did carbon tetrachloride last week? Remember doing carbon tetrachloride? Yeah, and it's non-polar, but it's got 4 chlorines attached, and they're relatively large atoms. So carbon tetrachloride is actually a liquid at room temperature. It's not a gas because it's big enough that it sticks to itself well enough that it's a liquid at room temperature. Okay. What about that one? Are you guys, that's more like last week's lecture than this week's actually, in a way. So what I'm trying to get you to see there is, like, for hydrogen fluoride, we've got this, and you know that, okay, fluorine's got 7 valence electrons. There's 1 there. I'll just put it as a cross so you can see it a bit more easily. So it's got 7, so it must have 3 lone pairs, and in this molecule there's 1 available hydrogen and 3 lone pairs, and I guess that harks back to that whole thing of, in the neighbouring molecule you've got 1 lone pair, you've got 3 lone pairs, but you can only really use up 1 of them to forming a hydrogen bond with a hydrogen on a neighbouring molecule. Yes, Samantha. Are you okay? Do you want to ask some more questions? Oh, okay, cool. I'm just going through the rest of these questions, but unless you had something else burning to ask. Yeah, all good. So I will see ya. No worries, no worries. Okay, water molecule, 2 hydrogens, 2 lone pairs. Yep. Ammonia, 3 hydrogens, 1 lone pair. I got to do something other than HCl. I'm over it. Okay, London dispersion forces. Okay, I put this one in because I know this is a mouthful, this temporary dipole-induced dipole, but it actually perfectly describes what a London dispersion force is. Okay, so I just put that in just to remind you. Yeah. I mean, you'd imagine that I'd just thrown you into the deep end with this stuff. You'd look at that and go, what on earth is going on there, right? But it's just telling you what's happening. All right, bigger the R, the stickier you are. Okay, to some degree, you guys could do this in lecture 2. In lecture 2, we were looking at molecules like this, and I used ethanol as the example and said, well, that hydrocarbon part there's non-polar. Look at your periodic table and other information. That's exactly what I've got there. That OH is polar, right? So remember we did like prac 2 one way or another, either in the prac or, online, where you did things like that chromatography, right? And we're looking at things sticking to one another, being either polar or non-polar. Okay, so the only difference now is we just nuanced it a little bit. We now know these OH groups here can form hydrogen bonds. And we know that the forces that are referred to when you're talking about these non-polar regions are called dispersion forces, right? So that's all we've done there. We just, got the fine-tuning knob out a little bit. Okay, I put this one in for you guys because I don't want you to forget about ionic compounds. Now, this whole lecture has been about molecules, and it's not unusual for students to get to the end of the chemistry course and then forget that there's a whole class of compounds that are ionic. And they are our friends. Well, they can be anyway. And so I just wanted you to remember back that a compound like this is ionic, and it has a that is absolutely true, Robert. They indeed have very much. Hang on, let me go back. What do you say again? Yes, that is indeed true. That is indeed true. So by the way, if things are covalent compounds, they form molecules. They're either going to be stuck together with dispersion forces or hydrogen bonds or dipole interactions or something like that. They're never as strong as covalent bonds, right? Having said that, you can get materials that are made purely with covalent bonds that aren't molecules that then have very high melting points. So, for example, diamond, but that's because it's a network solid. Okay. Alrighty. That was my shot at HCl. Nah. You can't form hydrogen bonds. Okay, that's an unusual question from me, by the way, because that's essentially a definition question. The definition of hydrogen bonds is they only arise from nitrogen, oxygen, and fluorine and hydrogen. Okay, so this guy here doesn't form hydrogen bonds. Even though it's got lone pairs on that chlorine, even though chlorine is very electronegative, it's not forming hydrogen bonds there, right? Okay. All right, we talked about that earlier, how you can do the experiments on this stuff and figure out what's going on. Everyone okay with that term elemental halogen? What I mean by that is F2, Cl2, Br2, I2, right? Those diatomic molecules there. In other words, when you're referring to something as the elemental form, it's how it occurs naturally. Okay? Sometimes that ain't so easy to if I talk about elemental carbon, although you just assume if it's elemental carbon, we're talking graphite rather than diamond. But anyway, they're both elemental forms. And that last one there is just making sure you got the units right for pressure, okay, which is the force per unit area, which is about the second slide in that lecture presentation. Okay. Are we done? Are we all good?
Can I ask a question about the assignment practical report thingy?
You most certainly can. Even about the fact that it's a thingy.
I just didn't know how to describe it properly. I'm sorry.
That's absolutely fine.
I was a bit unclear based off the information. What components we actually need to complete to do it? There's like this quiz thing that's lots of answer questions, and then there's the online titration PDF.
Well,
is that all we need to do for that?
Yeah, that's a very good question. So what I'm going to do is, can I just quickly walk you through this thing, because we've got time. By the way, if people don't want to listen to my wisdom in relation to this, I'm absolutely fine. You're more than welcome to go if you wish, but if you're hanging around, you're more than welcome as well. Okay, so, okay, we're talking assessment. And we're talking just simply called practical report, although I am tempted now, I can't help myself, Lillian, I'm so tempted to call it the practical report thingy.
You're embarrassing me now, you know that, right?
I am awful. I really am. Okay, so now let's look at this. Okay, so task. Based on a level 1 online titration simulation from the Royal Society of Chemistry website. So if you click that link, that will actually take you to the thing where you actually have to do it. So my first word of advice here is, when you go there, it will say to you, you can either just quick start, or you can get a login thing, right? I would strongly suggest you get the login, because you can do it as you go, save it. Now, actually, I will also strongly suggest, when you get your login number, go old school and write it down, because you won't get to see it again, and there's no password retrieval or any of that stuff. So you need that login, okay? Now, as you do it, it will automatically fill out a workbook. Okay, so and it will save it, and then you can do it at your leisure, and then when you've finished it, you just simply download it. Okay, now the next thing I will say to you that's of great use is that when you then go into the report, which is here, let's have a look at it. Now, by the way, it says in the instructions, ignore that it says it's a test, because that's just Blackboard, and there's nothing I can do about that. And if you go in here, and the first question is upload your lab book PDF. Yep. So it's not actually a question, it's a task. But Blackboard can't handle it any other way, so it's called question 1. So you upload it. Now, and all you do is find it and upload it. Now, this bit you should be aware of. We aren't going to care if you don't get full marks. We only, because it is actually marked, this PDF thing, we only care that you've done it, and we can see that you've had a reasonable attempt at it. So it could be a bit of a dog's breakfast, and you can't actually get to the end of it unless you successfully complete it. And every time you try to complete it and don't get it right, you lose marks. Okay, so do we care? No. Right? So don't spend 2 hours doing the darn thing. Because the other thing is, well, you guys should spend 2 hours, but not me. I mean, when I did it, I didn't get full marks because I didn't know what they wanted half the time anyway, right? You've got to kind of fiddle around with it. It's not the same as me being in a lab, working in a lab. It's online, and so therefore it's a bit more constrained. Okay, so anyway, so is everyone cool with that? All right, great. Now, all we're doing in this report then is we're basically breaking up this series of questions into sections. Okay, so this first question here is just getting you to understand that that's indeed the case. And we're doing this because it's supposed to mimic, at least to some degree, what you would normally expect in a scientific paper. Okay, so we're just trying to give you an idea of what scientific papers look like and their format and what goes in them, basically, right? So that's why I've got this one. Now, this question here is simply matching. So if you pull this down here, what is it? The abstract, summary of the main parts of the report, so that's 3, the introduction, gives rationale of why the work was done, that's 2, the methods and materials describes how it was done, that's 4, the results describes what you found. My goodness, I'm giving you the answers. Is this such a good idea? And the discussion explains what it all means. Okay, so that's 5.
So is this like quiz thing on Blackboard? I'm using that Blackboard, God. Is that basically in lieu of us actually going out and writing a report on like Word or something?
Well, you are kind of writing it.
Structured for us?
See, the thing was, because what happened was it was getting really stupid. What was that? Our fault, right? Because what was happening was that we were saying write this report, and then we're telling you to do all these sections, and then you're writing this report in sections, putting it all together in one bit, uploading it in one bit. And then we've got to go through and mark it in sections again. And that seemed nuts because you've got to mark each bit separately, right? And I said, why are we doing this? Why don't we just have it in sections to start with and just mark it? So that's why we're doing it like that. It makes life easy for everyone, right? Okay, so this question here is just to do with the safety data sheets, and that's another one. You can go through. That's another matching one, okay? And then, now we're going to do the materials and methods. So to start this materials and methods section, I thought it would be a good idea to start with a question that made it clear what the materials and methods actually does. So, of course, what it does is it's that one. What do we do? Right? Okay. Now, this one here, this is where you've got to start using your brain a bit. Okay, now you did, assuming you've done the online titration, there's a part in there that says something about sampling sites, right? So you need to write a title, selection of sampling sites, and then write what you'd expect to see written in the materials and methods for this. So there's no results, it's just, we sample, 3 samples here, 2 here with this transect or whatever you're doing, right? That's your methods and material. Okay, thanks, Emily. That's your methods and materials and stuff, right? Okay, so you've done that one. And then it says, okay, you've got to prepare a standard solution of sodium hydroxide. So this will be the one where you do that, I can't even remember now. It's been a while since I've done that. Royal Society thing, was the sodium hydroxide standardized first with something, oxalate or something, just like we did in the prac, whatever. Anyway, so you explain all that there, and okay, so now look what happens. results. This is the start of the results section. Then you do your results. Yeah. What is in the results? What do we find? Then you do your results section as per this, etc. Now, the good news here is that at any time, if you just click Save All Answers, you can come back to it. Now, the bad news is you don't get to see the answers to these questions. Okay? The good news is the first time you do it, why don't you just go through and click them all and figure it all out until you get them right. Submit it. Like that. And check them. Oh my goodness, I got them all right. Look at that. And you've got them there for you. So you could then do them anytime, but the other ones are the ones you might want to, like from then on, you might just want to click, because you can do it again, right? You can just do it again. So you can just...
Do you only mark the last time we click on Save and Submit, or like the best? Yep, okay.
Yep. And so what we're going to do is that the deadline's 5 p.m. Friday, week 13. So sometime after that, I'll put a password on it so you guys can't keep because I've got to eventually lock it off, right? So that I can then, people can then get in and mark it, and they know they're actually marking the latest version. Okay, that's the one we're marking. All right, and we'll just go in and look at it, and away we go. So does that help?
That helps immensely, thank you.
Okay, no worries. So the prac report thingy. You're a bad man, Robert. The prac report thingy has no time limit, none. So it says test, but it's not. It's an assignment. The only time limit is that deadline for submission, and then after that, we'll just start marking it. Is there anything else I can help you guys with? Alrighty, so yeah, don't forget also I sent an email out, as some of you may have joined a bit later than when I first mentioned this. I sent an email out to everyone in the whole course beginning of this week saying next week, of course, is the mid-semester break. I'm actually available 2 hours a day by appointment to help you with that prac report. So, but that one's not a drop-in. Just flick me an email and let me know when you're available and I'll make sure I'm there. Okay, that's via Zoom. Just look at the instructions in Blackboard and you'll be fine. Rio should also, I think, be available next week. I'm not sure. I haven't asked him yet. It'll depend a bit on what's happening. By the way, it's all good with him. There's, it's all a good thing, but you know, it's a personal thing, so I can't really mention what's happening, but it's all good. Okay, well, if there's no other questions, I always like to hang around till the bitter ends, so, and then let you guys sign off just in case you change your minds halfway through and you need to ask me something. So I'll say goodbye and hopefully I'll see you again in cyberspace one of these days. Thanks, Robert. Thanks, Lisa.
Thanks, David.
Yep. Okay. Cheers, mate. Okay, thanks. Thanks, guys. Thank you. Okay. No worries, Brent. Okay.